Okay. I hope you can see the problems at the end of chapter 3 for the book by Octave Levenspiel, Chemical Reaction Engineering. I'm using the 3rd edition. So we'll use this time the formulas and the concepts together with the principles that we have covered. That way you will understand how are we supposed to use those particular formulas. Okay, so we'll start off with 3.1. Okay, let me just get a picture of what this. So when we go to our Jamboard, it would be, we don't need to go back to this particular part of our presentation, or my presentation rather. Okay, so for 3.1, you're given that if the rate, which is the rate of change of the concentration with time, is equal to 0.2 mole per liter per second, when C sub A is equal to 1 mole per liter, what is the rate of reaction when C sub A is equal to 10 mole per liter? And there's a note here that the order of the reaction is not known in this case. But you are asked to determine the rate of reaction when this particular concentration, or this is the remaining concentration of A, after some time that the reaction already proceeded. So let's go to our Jamboard and check on how are we supposed to handle this particular problem. Let me check. Share. Okay, I hope you could see the Jamboard. So we'll start with the, okay, we'll not annotate because I won't be able to erase. Let's start with the given. So for our problem, you're given that, you are given the condition, by the way. So you're given a pair of information, and then using that pair of information, you are to determine the unknown. So for the rate, for a particular reaction, which is equal to 0.2 mole per liter per second, this would be the corresponding concentration of A left after some time. Okay, you are required, so that's the pair of information that you are to use. You are required to determine the rate when the concentration of A after some time is 10 mole per liter, 10 moles per liter. So in this case, if I'm going to ask you, it's noted in the problem that the N, or the order of the reaction, is not given. So how would you start solving this problem wherein you don't know the N, but you're given a pair of information that you can use in determining the rate that is being asked? Do you have any suggestion? If you're the one who's solving this problem, how would you start doing it? Do you have any idea? Okay, so nobody is, you're silent. So since you don't know the rate, you don't know the rate law, you don't know the N, you don't know the K, so you write it generally in this one. So the rate law is equal to K times the C sub A raised to N. Okay, so I have here answers in the chat box. Ratio, miss. Find K, miss. Excel. It should be K times C sub A raised to N. I'd like to go with the suggestion of John Vincent Villares. You have to find the K. Because the K for this scenario that is given, in which rate is 0.2 mole per liter per second, when C sub A is equal to 1 mole per liter, will be the same at this particular condition because we are talking of the same reaction. So from the pair of information that I have here, I'll use that one. So I have 0.2 equal to K C sub A 1 raised to N. Okay, 1 raised to n, whatever the value of n would be still 1, right? So 1 raised to 1 million, 1 raised to 1 half, 1 raised to whatever number is still 1. So you can have here k is equal to 0.2. Because anyway, whatever is the value of n, this would still be 1. So this is your k. So Vincent is correct. Then after you have already the k, you can write here rate is equal to, you get the k that you have here, which is 0.2. And then you have c sub a raised to n. It's still n because we do not know what n is. Then you substitute the corresponding Ca that is given here, which is 10 moles per liter. So you have here 0.2 times 10 raised to n. So your rate in this particular problem is dependent upon the n. So that's your answer. A general answer for that particular problem which does not give you the n. Now, if you could see here, I did not give any unit for the k. Why is that? Because we do not know the n. Remember, this k will have its set of units dependent on what is the order of the reaction. So we keep it like that. Or if you want, you can really write there as per unit time. And you can have here mole per liter. So based on our formula, this is raised to 1 minus n. So this is the set of units for your case. Still general because you do not know what your n is. Okay? So this is for problem 3.1 from level speed. Do you have any question? So sometimes class, it's in kinetics, there are instances wherein your answer will be an expression. It's not really that you are to force yourself to come up with an actual quantity or value when there are informations that are not given or there are missing information. So you have to express your answer based on that missing information. Okay? So we'll go back to the problem, chapter and problems. You don't have any question. So we go to 3.2. Liquid A decomposes by first order kinetics. So what is good about this is it's already stated that you have a first order rate law. Your reaction is first order. And it's to be facilitated in a batch reactor. And 50% is converted in a 5-minute run. How much longer would it take to reach 75% conversion? So what is good about, again, the problem is that you're given already the order of the reaction. So we go back to our Jamboard and then solve this one. So we have here 3.2 given. Based on the problem that we have read, the first statement tells us that n is already equal to 1. Okay, and then it gave us a condition that you have 50% conversion. XA is equal to 0.5 in a 5-minute run. So at T equal to 5 minutes. You are asked, based on this information, how much longer? So it's asking for the time when X sub A is equal to 0.75. Okay. Can you tell me what are we supposed to do? You can write your answer on the chat box and a suggestion on what we're supposed to do. What are we supposed to do? You're given already the order of the reaction, this pair of information, and you're asked for the time for this conversion. So what will you do? Aina, did you know what to do here? Aina,
Find K, miss.
we find K. Okay, how are we supposed to find the K? How do we find the K?
Using the first order formula, miss.
Okay, what formula is that? Can you dictate? In your case, class, since you're not having face-to-face classes with your teacher, whenever there is a synchronous discussion, you get important details or notes. Don't rely on the recording that you can go back to, because writing helps your memory recall easily the things that you need to recall. So there's a suggestion here from the Excel. You use ln of 1 over 1 minus xa equal to kt. Thank you, Dexel. So this is what you're going to do so that you won't have a rational argument for your ln. So you have it written like that, negative ln of 1 minus xa equal to k. So of course, it's very important that we get the rate constant because we already know the n. So using this pair of information that you have here, negative ln of 1 minus 0.5 is equal to k times the time, which is 5 minutes. So you will have a k value here equal to
0.186, miss.
ln of 0.5 divided by 5. Is it 0.1386?
Yes, miss.
Divided by, that's per unit time, which is in minutes. Because we have a first order reaction, then this is your k unit. Okay? Now you have already the k, then the rest is just substitution to the same formula. So you have negative ln of 1 minus xa this time is equal to 0.1386 times the time. So it's asking for the time when you have already 75% of A converted to the product. Okay. So your time here is 10. So you have 10 minutes. Okay, 10 minutes. This is the answer. It would take 10 minutes. So if we go back to this is the, shall I say, this is the answer for how long from the start of the reaction would it take for your A to be converted, or 75% conversion of A to the product. So it's important that we go back to the problem. That way we will answer the problem, what the problem is asking. Because in kinetics class, at times what you are solving is not yet the answer to the problem, but it's just pointing you to the answer to the problem. So I'll go back to the problems. Liquid A decomposes by first order kinetics, and in a batch reactor, 50% of A is converted in a 5-minute run. So why am I saying that you have to go back always to the problem? Because you're supposed to answer the problem specifically. So if you're solving for something at the sometimes it's not yet the answer to the problem. So you look at this phrase, how much longer? How much longer would it take to reach 75% conversion? So what should be your answer based on the question, how much longer would it take to reach 75% conversion? So the answer should be 5 minutes. That's correct, Excel, because it gave you already the scenario that at 50%, you have already, the reaction already, shall I say, started or has already commenced for 5 minutes. So how much longer, meaning it's referring to the original scenario. How much longer compared to 50% conversion of A? So your answer should be 5 minutes. So if you have answered, let's say for example, a simple problem as this, and you have answered 10 minutes, then you are not answering the problem, especially if it's just a multiple choice question. Then your answer will be wrong. But actually, you did not do anything wrong. It's just that you did not answer the problem based on the question that is being asked. So your answer here, I'll go back to the Jamboard, is not really this 10 minutes. So I'd like to erase here. So your answer should be, it would take 5 more minutes for A to be 75% converted. So this should be your answer. Though you cannot answer this unless you have solved for this. Okay? Any question? Now we go to the next problem. Now same problem, 3.2, but this time we're going to use second order kinetics. So take note, that this time I'm using problems that will use directly the pre-derived formulas using integral analysis for the two types of irreversible reaction. One is first order and the second one is second order. So since it's second order and the only species that is being mentioned here is A, then we have case. What case is this? Second order case 1, case 2, case 3. Can you still recall? You have a single species and it's second order. So it's case 2. Correct, Leah. It's case 2. So we'll now we'll use the same information that we have and then answer the required information. How much longer will it take for 75% conversion? So we'll first determine the K for this scenario we're in, N this time is equal to 2. So we'll have here 3.3. So you're given N is equal to 2, X sub A is equal to 0.5 at T equal to 5 minutes. Required time.
Excuse me, miss. Wala ka miss sa Jamboard.
Wala ko ka-share Jamboard, sorry.
Ay, okay, miss.
Can you see the Jamboard?
Yes, miss.
T when X sub A is equal to 0.75. So what formula should I use? Second order, case 2. Let's see. KT is equal to 1 over CAO. 1 over CAO times XA over 1 minus XA. So for case 2, thank you, Dexel. For your case 2, let me check. Okay, Dexel is correct. So 1 over CAO times XA over 1 minus XA equated to the product of K and T. Okay. Okay, so let's see. The problem did not give you any initial concentration. Whenever a problem does not give you initial concentration, don't panic. It's just a constant. So you can group that together with the K that you have in here. So what I mean is this. So substitute the XA, which is 0.5, And you have 1 minus 0.5 equal to the K together with the CaO. I'll place here. They're together, and then I'll multiply with the time, which is 5 minutes. So what I'm solving actually here will be the constant K times CaO. So in this case, this is already 1 divided by 5, so that would be 0.2. Right? So you go back to this expression, you have XA over 1 minus XA is equal to KCaOT. Then you substitute the KCaO value that we got here, which is 0.2. And for the time, that's a known, and you have here 0.75 divided by 1 minus 0.75. So that's it. You have 0.75 divided by 0.25 divided by 0.2. So your answer is 15 minutes. 15 minutes for 75% of A to be converted. So your answer is not 15 minutes. How much longer? It's referring to this first scenario in here from the 5 minutes. So it will take 10 minutes more for A to be 75% converted. Okay, so this is your answer. This should be the one that you're going to box whenever it's part of the instruction that you box your final answer. 15 minutes is your computed time. That means it will take 15 minutes for your A to be 75% converted. Okay, but from the 5 minutes, it will take 10 more minutes for that to happen. Any question? Okay, I'll go back to the problem again and we'll look for another sample. Okay, the others will be for multiple reaction. Okay, so you'll have a sample for the use of the empirical rate equation. We will have 3.11. Okay, can I ask, so we can have 3.11 and 3.12 because 3.12 will be using the information in 3.11. Can I ask for Josh to read the problem?
Aqueous A at a concentration of 1 mole per liter is introduced into a batch reactor where it reacts away to form product R according to stoichiometry A to R. The concentration of A in the reactor is monitored at various times as shown below. For the concentration 500 mole per cubic meter, find the conversion of reactant after 5 hours in the batch reactor.
Thank you, Josh. So this is your problem. It's giving you the T and the CA pair of data. So we can try using here the empirical rate equation, okay, without having to guess and test. Okay, we'll write first our given information. So this is 3.10, 3.11. So you're given the reaction. This is A being converted to R. And the initial concentration is, let me check. The initial concentration is 500 mole of A per cubic meter. Okay. Initially, the given concentration is not 500 mole per cubic meter, but based on the empirical set of data that is given to you, it's just 1 mole per liter. So this 500 mole per liter is for the required information already. So you have to be very careful. So it says here, aqueous A at a concentration CaO equal to 1 mole. So it's not cubic meter, but liter. Okay, so based on the empirical data, your units are in mole per cubic meter, but the information that is given for the initial concentration is mole per liter. Okay, it's a reaction of A forming R, and you are given this pair of T in minutes and CaO in mole per cubic meter. So you have to be very careful in instances like this wherein the given unit is not same as the empirical units used for your data. So 100, 500 here, you have 200, you have 333 here, you have 300, you have 250, and we have 400, and you have 200. Okay, now this is our given, but this time the required information is this. For a different CaO of 500 mole per cubic meter, find the conversion. So XA for T equal to, this time the time unit is in hours. In 5 hours. Okay, so that's our problem now. Now we go to our solution. So these are the information that we can use. So our solution will try to use the empirical rate equation. That way we don't need to go to guess and test. So what's the empirical rate equation? So we've discussed it last meeting. You have Ca raised to 1 minus n. We write it. You have Ca raised to 1 minus n minus CaO raised to 1 minus n equal to 1 minus n kT. Let me check if I have copied it correctly. Or it's n minus 1 kT. So it's n minus 1 kT. Somebody wrote in the chat box. Correct. I got it interchanged. So n minus 1 kT. Now, how do we use the empirical rate equation? We assign a value for n as long as that n is not equal to 1. So this equation will not work if n is equal to 1. Same thing if it's 0, then you might as well try to use the integral analysis equation for 0 order na lang if it's 0 order. So in this case, we cannot use n equal to 1. So we will try to have an expression here that will solve for k. That way we can assign value for n, or we can assume an initial value for n and check whether based on our pair of information, it will not change. I'm referring to the k value. So I will have here Ca raised to 1 minus n minus CaO raised to 1 minus n divided by n minus 1 times the time. So this is our working equation now. So assume. So we will make a first assumption. Okay. Since we cannot have a 1, then we will have a 2. Assume n is equal to 2. Okay. Based on our information here, we'll take pairs of data here and check whether our K will not change. So this is our initial concentration. This is initial time 0. And in CaO is 1,000 mole per cubic meter, which is equivalent to this. Okay? You can check that. Your 1,000 mole per cubic meter is equivalent to 1 mole per liter. Okay? So initial, let me just use a different color. This one, this pair refers to this. The initial concentration of A. Now we go then to the next information here because we cannot use the initial concentration anymore. Because anyway, it's a constant. So we can place the CaO in terms of mole per cubic meter, which is 1,000. Now, we go back to that black ink there. So we use the 100 and the 500. Okay, so here, for 80, which is 100 minute, is it minute? Yeah. And Ca equal to 500 mole per cubic meter. We'll solve for the K. So your K is equal to, let's have it as K1 based on the first pair of data that we use. So we have here a Ca of 500 raised to 1 minus 2 minus CaO, which is 1,000. I'm using the unit which is in mole per cubic meter. 1,000 raised to 1 minus 2. And I have here 2 minus 1 times the time, which is in minutes na lang. So we'll have 100. So you have a K1 value here, which is, can you solve? Your answer is 1 times 10 raised to negative 5. Okay, 1 times 10 raised to negative 5. Okay, everybody got that answer. So this is our K1. Now we go to K for the second pair of information. So for time, which is equal to, this time I'll use the second pair here, 200 and 333. So I will have here 200 minutes and the Ca, which is 333 mole per cubic meter. So same thing, K is equal to, so based on our formula, we will have 333 raised to negative 1 minus 1,000 raised to negative 1. I just used the 1 minus n right away. So I simplified it already. Then you have here over 2 minus 1 times a time of 200. So your value for K, I'll have this as K sub 2. Okay, 1.0 times 10 raised to negative 5. Okay, more or less same as your answers before. The difference is, the difference is just the 015 here. It has here 0015. Okay, I'll just write it that way. Okay, now let's try with another one, another set of value. For t equal to 300 and 250. 300 minutes and Ca, which is 250 mole per cubic meter. So K3 is equal to 250 negative 1, 1,000 raised to negative 1, 2 minus 1, and I have here 300. I have the answer here already. The answer is 1 times 10 raised to negative 5. So see, let's see, we'll have for the last one, for t equal to 400 and 200. So I'll have here 400 minutes and C sub A, which is 200 mole per cubic meter. Your K4 is equal to 200 raised to negative 1 minus 1,000 raised to negative 1, 2 minus 1, and I have here 400. Let's see if it will be the same. Answer is 1 times 10 raised to negative 5. Therefore, based on this, since your K did not vary that much, your assumption is correct. Therefore, we say N is equal to 2. Okay, we know already that n is equal to 2. If n is equal to 2, then you have the rate equal to k c sub a raised to 2, right? Now, this is already your rate law. However, if you write it that way, you still do not know this one. Okay? So how will you find the k in this case? What's your rate constant in this case? How will you find rather the rate constant? You will, what will you do? Second order case 2, right? This is second order case 2. We only have one species. Then what do we do to find k? What will you do if I'm going to ask you? What will you do, Fritz, to find k? Fritz, are you there? Okay, somebody wrote 1 times 10 raised to negative 5 hindi na sa imo, hindi na sa amo, miss. Okay. Sige. So, Fritz is awake this time. So, he's not sleeping or he's not eating his lunch. Okay, so K is 1 times 10 raised to negative 5. Very good. So, you have K equal to 1 times 10 raised to negative 5. Now, how do we find what the problem is asking? John Albert, the problem is asking for the conversion after 5 hours if this is the initial concentration. By the way, John Albert, what is our set of units for RK? It's second order.
Moliliter, miss. Ay, moliliter over, ano, miss, minute.
Again, you want the? Is it moliliter?
Wait, or minute squared, miss. Or minute squared.
No. You always have time raised to negative 1. So meaning you have here already per minute. What would be the other set of units that should go with the per minute?
Liter siya, miss. Hindi. Like, second. Wait.
It should be cubic meter per mole.
Mole.
Cubic meter because our empirical data is in concentration is mole per cubic meter. So that's our K. Now then we are ready to solve for what the problem requires. So the problem requires us to solve for conversion after 5 hours, starting with an initial concentration of 500 mole per cubic meter. What do we do? Patrick, what do we do? Case 2, second order. Patrick, are you there?
Yes, ma'am.
Oh, what do we do, Patrick? We
Use
want
the formula.
Okay, what's the formula? Can you dictate?
Negative RA is equals to KCA squared.
We know already that this is our rate law. Okay, so I'm asking for the formula that we can use to find the conversion after 5 hours. What formula are we going to use for second order case 2?
KT is equals to 1 minus CAO multiplied by XA over 1 minus XA, miss.
Okay, 1 over CAO. Sige, Patrick. You have XA over 1 minus XA equal to we'll have the K here, 1 times 10 raised to negative 5 T. So this is our formula. So we'll use the given, which is 1 over 500. That's the initial concentration for the required, not the 1 mole per liter, but this time it's 500 mole per cubic meter. So we'll have here XA over 1 minus XA equal to 1 times 10 raised to negative 5. Your time, which is in 5 hours, needs to be converted to minutes because our unit here for time is in minutes. So you need to multiply this by 60. Okay, that way your units now will be agreeing. So your conversion is equal to okay. So you have the answers here. 0.6. Okay, so this is our answer. Now, if we go back to the problem, find the conversion of the reactant after 5 hours in the batch reactor. So meaning this should really be our answer. Okay, so I'll box this one. It's asking for the conversion of the reactant after 5 hours. Okay, somebody wrote in the chat box, yes, it's 0.6. Now, for 3.12, find the rate for the reaction of problem 11. Okay, the rate for the reaction of problem 11. So what do you think is this rate that is asked here? Okay, I will annotate. What do you think is the find the rate for the reaction of problem 11? What rate is it asking for? Rate law, rate equation, or simply the rate? As in a value for the rate of the reaction or an expression, a formula? What do you think is it asking? Find the rate for the reaction of problem 11. Let me check. What do you think, Dia? What do you think is this rate? Is this rate law or rate for the reaction of problem 11 is a value?
Value, Miss.
A value, correct. It's a value. Because if kinetics will ask you for the rate law or the rate equation, it would really say you, it would really state that what is the rate equation or what is the rate expressions. Okay, so we go to our board and then determine what this is. So for 3.12, what would be the rate in this case? So you have KCA squared, right? So you have K is 1 times 10 raised to negative 5. What CA will you substitute here? What CA will you substitute? John Vincent Millares.
1.6, Miss. Hindi.
Conversion na iaiho ang 0.6. So what CA will you substitute?
500, Miss.
That's CaO. Initial concentration na iya. So what CA will you substitute here? Ezra. What CA will you substitute here? They should give you already. What should that be?
$100, Miss.
Why 100 Ezra? Isn't this Ca, CaO, 1 minus Xa? If you use that, how will you answer here? What will you answer here? You will have 500, 1 minus 0.6 quantity squared. It's asking for the rate in problem 3.11 based on the question that it answered. So you answered for the degree of conversion. At that particular degree of conversion, it's asking for you the rate of reaction. So in this case, you will have 1 times 10 raised to negative 5. This will be 500 times 0.4. So correct. That should be 200. 200 squared. So the rate that is being asked here is 0.4. So Drexel is correct and Fritz for the 200.4. Correct. 0.4. What should be our set of units here? 0.4. What's our set of units for the rate? Jericho, are you here? Okay. Jericho is out. The in and out siya. Drexel, rate, not rate. Why is it per minute? Rate, unit for the rate of reaction. Patrick, what's the unit for set of units for this rate of 0.4? Vincent, Lucky. Patrick, what's the set of units for this? Isn't it that rate is the rate of change of the concentration with respect to time? So what should be the set of units for this? It's 1:30 already. Bia, what's her set of units for this? Lacking. Aina, what's her set of units for the rate of 0.4?
Mole per minute m cube, Miss.
Very good. Mole per cubic meter is for the concentration. Per unit time, which is in minute. That's your answer with the correct set of units. It should be mole per cubic meter per minute because rate class, especially if it's for a single phase liquid system, it's always concentration divided by time. So mole per cubic meter per minute. Okay? Any question? Stop sharing now. 1, 2, 3. There's only 7 of you. Jericho came up. Johan,
Disconnection, Miss, at Jericho.
gani, na-disconnect siya, I know.
Si Johan man miss na disconnect man.
Johan. Sige. Okay. We will continue tomorrow. So you have already your examples for the principles. Then we will continue with the other concepts tomorrow. Hopefully we can reach multiple reactions. Okay? You have any other concerns?